Next up, we have Rowan McAllister from Toyota Research. Rowan did his PhD back in Cambridge University, which is where we met. Since then, he's done a postdoc with Sergey Levin on, I guess, on autonomous vehicle technology, and it's the same subject which Rowan works on now. So yeah, without further ado, Rowan McAllister.
Great, thanks so much. Let me see if I can share my screen. Can everyone, can you see this, Andre?
Yes, I can.
Great, okay. Well, yeah, thanks everyone for coming along. And thanks to Andre and the team for organizing this challenge on such an interesting topic. It happens to be a very critical theme for the research that we do at Toyota Research Institute. So I'll talk a little bit about some of the work that we've done here. As Andre pointed out, I've recently joined from Berkeley, and so I'll talk a little bit about some of the prior work that was done at Berkeley as well. And this is really around the kind of applications of autonomous vehicles. Okay, so chatting with Andre challenged me with these questions, and so I thought I'd organize the talk around these particular questions, which I'll go through in order. So the first one is, what are some of the main sources of distributional shift that we might see in autonomous driving scenarios? So there are multiple, obviously, but some of the ones that I think are common that we wanted to look at in terms of distributional shift, but also the kind of long tail of uncertain scenarios, things that aren't necessarily outside the distribution, but that are just very rare, which is a very related problem. Are things like temporary changes to road networks. So things like construction zones, or we may have kind of unfamiliar intersections. So especially if we go to a new geographic area, North America, for example, may not have many roundabouts, whereas roundabouts can be more common in Europe. And so if we were to ever deploy something, going over state boundaries or national boundaries, we may see a lot of distributional shift in the way that the road is organized. Humans are probably the biggest source of stochasticity when it comes to autonomous driving. So this is true in robotics as well, but with human drivers around, they're always going to do something that we don't expect. There's a lot of uncertainty about which way they will go as well. At Toyota Research Institute, TRI, we see all sorts of interesting things in our logs. We see people doing illegal maneuvers, driving down the wrong side of the road. It's rare, but you need to be able to react to it. And so often these distributional shifts, they're not actually the fault of the autonomous system itself. They're just presented with something, and often there's no such thing as no action. So especially if we're going at speed, we still need to be able to make a decision, even if we're in an out of distribution situation. Often there's no give up option. We still need to make a safe decision, given that the safety critical nature of robots on the road with humans present. And something that that we've seen kind of recently is like there's changes to the way mobility happens on roads, right? So like electric scooters have been a recent thing that have changed. Maybe they aren't in our thousands of hours of data that we've collected, if that was a few years ago. And now there's this scooter which seems to be faster than unpowered scooters. It's very strange from maybe a modeling perspective if we didn't have this class in our data set so far. And other things like one-wheeled skateboards. There seems to be a new form of mobility every few months. And so the landscape is constantly changing, which makes things interesting. So now uncommon does not mean unimportant. So, you know, uncommon things can be disproportionately responsible for the safety infractions and also discomfort for the human occupants inside the car. And there's also this question of fairness. So the long tail includes underrepresented regions as well. So you know, we don't necessarily want to build our machines that operate well wherever the engineers happen to live and work. It kind of, you know, we want to be able to build these machines that work well for everyone. And so a couple of the things I'll talk about in this talk, coming back to these themes, is that we've got a big potential to reduce, you know, safety infractions and failures for learned systems that can better generalize from their offline data sets and can also better adapt to the new data that they're seeing online in the moment in real time. Okay, so one work I wanted to talk a little bit about is this collaboration we did with Oxford. This was spearheaded by Angelos and Panos. And this was a question about, you know, can autonomous vehicles first identify and then possibly recover from, and additional, can they adapt to distributional shifts that may be occurring? So this is following that middle example I was talking about on the slide before in terms of geographic distributional shift. So here what we're seeing is a benchmark data set that Angelos and Panos put together, which is comprised of interesting intersections in the Carla simulator world on some of the towns 3, 4, and 5. So if we train our models off more Manhattan grid style towns that they have in town 1 and 2 in the Carla simulator, how would these models, you know, work if they are confronted with things like, I hope you can see my cursor, but things like 45-degree turns or roundabouts or kind of more 3D landscapes with hills and so forth. So here, for example, is a simulation of a roundabout. Here we have a video clip of a 45-degree turn that the model has not seen before. It's only seen 90-degree turns. And so first of all, the way in which we approached this problem was to kind of embrace uncertainty in terms of using an ensemble of models. And we came up with this algorithm called robust imitative planning. And it uses the principle of pessimism under uncertainty. So we started off with using an imitative model, which looks something like this. So can we plan according to something that argmaxes a set of state predictions trained on an expert model, a model of expert human drivers, on what state trajectory they would have taken given a goal that they're trying to get to, and given some context of the scene. So this can be LiDAR or vision, and this should say posterior, sorry. So in the imitative modeling framework, this can break down into 2 terms. So by Bayes' rule, we've got a prior term and we've also got a likelihood term, and the normalization term cancelled out. Now, in the robust imitative planning framework, what we could do is we could use an ensemble of models. So we can randomize this element Q here and say we may actually have a collection of 5 models. And the planning under the principle of pessimism here is to say, can we take the best worst case trajectory to follow? So what this means is that all of the models are going to hopefully be agreeing around where we have data. But if there's any actions if there's any particular state trajectories in certain contexts that we don't have a lot of data for, we don't know how a human would maybe take a particular turn that way. What this will do is it will basically search up for the worst case scenario and suppress this model wherever it starts wherever the optimizer starts looking at states that we really don't have that much data for. So and so basically it tries to come up with the best worst case scenario. And has an adaptation rule if the variance of the ensemble exceeds some threshold. So this is kind of Bayesian-like, where we have disagreement between models, where a proper Bayesian posterior would say, I'm quite uncertain away from data, and we get a similar effect with using ensembles. And so what we find is that, for several reasons that are actually still kind of unclear to us, is there are certain generalization benefits from just doing the initial robust imitative planning without even considering the adaptation rules. So things like abnormal 45-degree turns, things like roundabouts, these robust imitative planners often outperform just the basic straight deep imitative models using a single model. But one of the real benefits comes through here when we can ask a human driver, if we know we are uncertain about a particular course of action, say at the roundabout, we've never seen this particular context before. When the models disagree, we know this is a good time to ask the human if they are able to provide a demonstration for us in this instant, without burdening them, asking them too much, but asking them in the situations where we really know we need data. And so it turns out for problems like this, when we're kind of doing this style of active learning, we can really learn very quickly. Just using 2 or 3 demos from a human driver on how they would have navigated the roundabout or the hill or the 45-degree turn. Okay. So the second question is, how does this affect individual components of the AV stack and overall? So some work we recently did with our colleagues at Stanford that was spearheaded by Boris, and this was part of Marco Pavone's lab, was this topic of heterogeneous agent trajectory forecasting by incorporating class uncertainty. So what we're trying to do here is we are trying to allow uncertainty to propagate down the stack of the autonomous vehicle. So normally we have, a kind of a very common stack is to separate things into perception and then, forecasting or prediction, how other agents on the road may move, and then maybe after that, robot planning. It's not the only way to do things, but it's a common one. Anyway, this work was about, how do we take perceptual uncertainties and really use them downstream, and in particular the class uncertainty about what it is that we are seeing. Is something, are we seeing something like a pedestrian or a bike or a vehicle? Now, in many situations, it's obvious. Perceptual systems are, the deep learning revolution has hit that first, the perceptual component, and now a lot of perception systems are obviously very good at identifying these things, but not always. And so there's instances like at night, the death of Elaine Herzberg was the first pedestrian death by an autonomous vehicle. It was at night. The LiDAR was able to see the pedestrian, the vision was not. And if you read through the crash report, it's very interesting. But what happened is that the class uncertainty was changing rapidly, and because the class uncertainty from the perceptual system was changing a lot, the forecasts were changing a lot, and the car wasn't able to predict that they were on a collision course. So, to be, good Bayesian stewards, what we should be doing is projecting that uncertainty downstream from the perceptual systems through. So, if we have, logits that come out from our perception system, on what class that we might be looking at, if we can input that into some kind of auto-regressive trajectory forecasting model, then that at least allows the model to consider the fact that it's, what it may be looking at here in terms of these past trajectories of, say, itself together with another human. Um, uh, it it can consider all the hypotheses, not just the most likely hypothesis about what it is that it's seeing. Now, this is actually important when it comes to training and it comes to out of distribution situations, because what happens is we can get support over everything that this class probability may be in terms of our trajectories that are predicted downstreams. So usually with these class logics, there's usually no class that's absolutely zero probability. There's usually always some probability that any particular agent could be a cyclist, could be a truck, especially at night, or other instances like fog when we're not quite sure. And so an example here is if we've got this particular trajectory and we've got a vehicle, and this is the truth, we've classified it correctly, then our predictive model will predict, this is using Trajectron++, by the way, will predict a sequence of trajectories like so. But if we were to incorrectly predict what the pedestrian would do, we get these crazy predictions. And so by at least allowing the model to have support over both of these hypotheses, that, yeah, sometimes it could be a pedestrian, we can get better tuned models that account for all of the hypotheses about what the perceptual system may be seeing. And so we had a look at the LIFT level 5 data set and also generated our own. The LIFT level 5 data set, I think, is the first data set to publish with class uncertainty. I think it was maybe logits, or basically a representation of the different class uncertainties about what it is that it is seeing. And so that allowed us to test out this model, which was a generalization of Trajectron++ on, which is here as one of our baselines, on how does it do on some of the ADE and FDE, so average displacement error and final displacement errors, but also the probabilistic analogs with the average negative log likelihood error and the final NLL error. But one of the things that but to really test this properly, what we had to kind of do is figure out basically a new data set that was a little bit more biased towards the situations where we do have the uncertainty. So often in most data sets, it's quite obvious that something is one class or another class with like 99% probability or whatever. But we find, when we bias the data set to kind of extract some of the more interesting scenarios, that's when we get bigger performance differences. And so this data set, PUP, which stands for Perceptual Uncertainty and Prediction, essentially we have more balance in terms of different types of classes, but also the entropy on those class probabilities is much higher. So this is using our own perceptual systems, both on this data set and also the LIFT level 5. On the LIFT level 5 data set, we're quite certain what everything is most of the time. There's very low uncertainty. But in the scenarios where we've extracted the more unusual cases, we were able to basically isolate this to really kind of test models on uncertainty propagation. So that's the PUP data set if anyone's interested in it. All right. So what has been done and what could still be done to improve robustness? Okay, so I want to talk about kind of two concepts on how we think about things. So basically, often what we deal with, and especially at Toyota, we've got these kind of offline data sets on people driving cars before, and can we use that for a computer to control a vehicle at deployment time? Now, one thing that we've kind of always anticipated is that whatever data we're collecting online is possibly going to have some kind of distributional shift for a variety of reasons. Maybe we're not taking it back to the same spot that the human demonstrators gave us data. It's usually in the future compared to the offline data set collection. Well, it's always in the future compared to the offline data set collection. Things can change, so forth. So we kind of treat distributional shift as inevitable. And so, okay, so there's two kind of ways that we think about how do we deal with this. So the first of all is, can we generalize? So from this distribution of this blue distribution of data here, how far can we generalize beyond the distribution itself and still have models that are applicable to maybe slightly outside the distribution? Or if we're getting quite far outside the distribution, can we adapt to the new data online? Excuse me. So if we treat distributional shifts as inevitable and unavoidable, then generalization for prediction and planning models is one avenue forwards. And there's several ways to improve generalization, I think. So this isn't necessarily about our own work, but this is kind of our philosophy about the ways to go in the future and what we're interested in working on and what many others are interested in working on. So there's several ways to improve generalization by learning higher level abstractions for offline data or abstract relationships. So the first is kind of using domain priors or inductive priors. So this includes things like dynamics priors by incorporating like known robot physical equations into learned dynamics models, or maybe some kind of causal structure to mitigate issues of causal confusion with correlations, or maybe kind of objective priors that different agents are trying to optimize from things like inverse optimal control. So for AVs, I think we do want this human knowledge. So this is kind of going against the things like the bitter lesson that Richard Sutton and others kind of propose. I think in the case for autonomous vehicles, it does make sense to use all of these things, especially because it is a safety critical scenario. And so really anything that is kind of gives us a higher level relationship or abstraction that kind of holds true across many situations. Another way is desensitizing representations or models to irrelevant signals. So this can be training representations from like demonstrations that retain only the information relevant to the downstream tasks, which are, is perhaps prediction or planning, and to learn insensitivity, like an insensitivity and robustness to other forms of like superfluous information and non-causal correlations signals to compress scene representations and thus limiting the kind of frequency of domain shift happening in the first place. Adaptation is also important for larger distributional shifts that go well beyond the distribution of offline data that our model was originally trained on. That may not be able to be remedied by generalization techniques alone. So yeah, to better adapt to new situations, we can use uncertainty-aware models to first detect when or quantify how far a robot is outside the distribution of offline data that's collected so far. So basically the model has a chance to temporarily weigh the online data that it's collecting, which may only be a few seconds compared to maybe the thousands of hours that it's collected offline, if that online data is much more relevant to the task at hand. So once this distributional shift is known to be occurring, we can then apply several techniques to do online adaptation. One was an example that I was talking about with the Carnival paper before on being able to ask a human at the time. Another form, if we don't have a human to ask, we can kind of ask indirectly through third-party imitation for social changes. So that example of roundabouts, I think that's actually how a lot of humans kind of adapt to new situations. So if I've never seen a roundabout, I've grown up in North America, I go visit Europe and get a rental car, I typically don't don't crash when I see a roundabout. And there's a variety of reasons there. One is that I've got a high level understanding of what curbs mean. So even though I've never seen a circular curb, I still understand it delineates the edge of the road and I shouldn't be driving over it. But second, it can still be confusing. And one of the things that can help is if there's actually other drivers on the road and you can copy them, right? And that few seconds of data that you're seeing is much more relevant than, the thousands of hours of data, of like driving that you've done previously in your life. So we hope to be able to kind of copy that as well. So yeah, okay. Without further ado, let me jump in and also Andre, please let me know if I end up running a bit over, and I'll wind up. So I wanted to talk a little bit about a couple of the ways that we achieve better generalization through this desensitivity. So trying to desensitize our models to things that really don't matter. So, okay, so one example is, consider you're an autonomous car and, you're trying to look around at this scene. There's a few people around and we want to be able to predict where they'll go. So it seems like these people, they're kind of walking into the direction that we want to travel. So it seems that it's probably going to be important to focus on them and to anticipate where they're going to move next. Now we could consider this pedestrian over here. And maybe say we make a prediction that the pedestrian walks this way, but the ground truth is actually that this pedestrian walks out that way. Now, the question I want to pose is, does that error matter? And I would say that error does not matter. If we make an erroneous prediction there, it doesn't matter with respect to the safety of the autonomous vehicle, as opposed to other pedestrians that we may predict that maybe they'll walk just a couple of meters in the next few seconds, or maybe they start jogging to make the lights and then they start intersecting with our vehicle. So this is obviously a dangerous situation, and we would like to be able to model that pedestrian, that third pedestrian, better than the second pedestrian. So some metrics that are often used in forecasting are shown here. It's not the only set, but it's some of the common ones. So like ADE, FDE, miss rate, and also for probabilistic models, we can use the likelihood of the negative log likelihood. And so that's what we'll be considering here. Okay, so for safe deployment of robots in human environments, the robots, they need to be able to have these predictive models. They need to be able to anticipate human motions to avoid collisions, which they can do with predictive models that typically regress to human trajectories recorded in data using those aforementioned metrics. However, the problem is that those metrics do not account for how the predictions will ultimately be used downstream, which is a common problem called objective mismatch. So the predictive models are trained on a metric that does not correspond to what we ultimately care about, which is safe driving. Okay, so our goal is to improve prediction accuracy where it matters. So for example, predicting this motion of a pedestrian in yellow here is quite important because it looks like they might be crossing the road, in which case we will have to act if we are this autonomous car in red here. By contrast, the predicting the closer pedestrian in green, even though they're closer to the vehicle, might actually be less important. If we're fairly confident they'll stay on the sidewalk, the exact route that they take on that sidewalk, we really don't care. And so it would be great if we could use knowledge of our downstream planning component to inform prediction relevancy, which we can do through a sensitivity analysis on each of the pedestrians, which is the solution that we take. And so the outcome is a predictive model that can be a little bit more accurate where it matters, and ensuring accuracy is best on motions like pedestrians crossing the road. Now, this is important in case other pedestrians do certain things that kind of crazy that we can't really predict. By desensitizing our model to pedestrians that are less likely to matter to the car, then there's less ways for distributional shift to really occur in the end performance of the vehicle in terms of its the quality of its planning, which is in this case dependent on the quality of its inputs, aka the predictions of where pedestrians will be moving. So a couple of ways that we do this is we use the R2P2 algorithm, the reparameterized push forward policy. So this is an autoregressive normalizing flow. So this is the as a baseline. And so its objective is the likelihood. And so we came up with a few ways to alter this. The first is to weigh these likelihoods in our prediction training by the L1 distance between so here is the autonomous vehicle planner, what it would have done given the ground truth information, with what it would have done if it was given a sample from the model on what the model predicts might happen. Now, if y is different from y hat, that doesn't necessarily mean we've made a kind of fatal error or an unsafe error. However, if what the vehicle would do is very different under both of those circumstances, then we know that prediction was very important to get right. So either the vehicle should have braked when it didn't, or didn't brake when it should have, for example. And we want to mitigate both those types of errors. We also tested with a more pessimistic form of this. So we would take several samples from our probabilistic model and take the worst case scenario. So maybe there was only a 10% chance that the pedestrian would step out on the road. And as long as we sample 20, 30 times, hopefully we'll at least capture that and be conservative. Another is to use attention weights. Now, I want to be upfront. This is actually concurrent work with many other works that have happened this year in 2021. Many other authors have also thought about this same idea of how to alleviate this objective mismatch problem, including for autonomous vehicles. One of the differences that we have here is that we make no assumptions about the planner pi here. So we assume that we're given a planner. It's not necessarily stochastic. So that makes it harder for policy gradient methods if they need to assume that a policy is stochastic, and it's not necessarily differentiable. So that rules out a lot of end-to-end kind of methods and any methods that do local sensitivity analysis. Here, what we're doing is a global sensitivity analysis. So this prediction doesn't have to be anywhere close to the ground truth. It can be all over the place. And one of the reasons why we're thinking down this line is that planners in real autonomous vehicles, as much as we want them to be end-to-end, coming from the machine learning world, they're often not. And there's several reasons. One is that it's a very safety critical component. Second reason is like a lot of the work done in planning, pre-deep learning revolution is often very good, and it's hard to beat, and it's interpretable, and it's easy to debug. And so there's all of these things going for not incorporating machine learning into planning. And so therefore they're not necessarily designed to be nice and differentiable. And so for real, at least for autonomous vehicle systems in the next 5 years, and the current state of things, we wanted to be able to come up with a predictive model that would be amenable to the planners used in the real world. So yeah, the attention, so that last method I talked about uses attention weights. So this is if we take several other vehicles, or in this case pedestrians, together with our own vehicle, and we learn the attention weights on how they all interact with each other. And what we select out here is all of the attention weights that all of the pedestrians had on predicting the motion of our ego driver. And and so what we get here is I'm showing the attention weights by the width of these lines here. So we've got multiple pedestrians around. Many of them are kind of closer to the vehicle, but this pedestrian's a bit further away. and they look like they're about to cross. And so the attention weight has learned successfully that this pedestrian matters much more than all of these other pedestrians. And this pedestrian may end up crossing as well. And so this is kind of what it looks like going down the street, what the car is most focused on in terms of how it will be driving. Does it need to brake or not if they step out onto the road? And this is what we can use to weigh our predictive metrics to get a better success rate. So success rate here means no collisions through an episode. And so what we can see here is our methods, they can do better than the baselines in terms of success rate, but notice that the average displacement error is not actually necessarily better. In fact, it's worse. So it's worse than the baseline here, but we got what we ultimately cared about, which was less collisions. So this is the real thing that matters, right? Okay, and I think, Andre, I might stop here. I think that's about time. Is that right?
Yeah, that's fine. I mean, like if you have anything else, I think you can go in for a bit more. But yeah,
Okay.
It's up to you.
Okay, great. Maybe I'll go on for another 5 minutes and
Sure.
talk about biosimulation. So we can also apply the same robustness qualities. The same kind of the idea of desensitizing our models to not just the component of prediction, but also the component of perception. So if we start off with this question, like, are all percepts equally important? Hopefully when there's if there's a particular task at hand, it becomes a bit more evident that like certain things just don't matter as much as other things. So in this case, we've got like clouds in the sky, houses over here, trees over here. Now these things don't really matter in terms of representing the visual scene about where a vehicle where a vehicle is and what it should be doing. So say we're in a first person point of view driving down a road and we see a car coming down the road. The car and where the road is are quite relevant to obviously avoid collisions and stay on the road. Whereas these things in the background are not so important. So can we actually say, given that the road is the same and maybe the car model type changed, but it's in the same position, can we come up with a representation or a latent space that actually maps these two things to being the same point? So whether there was a tree or a house doesn't really matter. It was functionally the same, these two images. Compared to this image where the road is going the other direction and there is no car, that is functionally quite different. And so can we come up with a latent space that, that says that is a different scene? And if we use this representation for a controller, it can then enforce that the actions taken in these two situations are the same, and it will ignore all of these things, but not in this case. Okay, so learning representations for control with biosimulation is this work. And so this was in contrast to other things like generative models, including like VAEs, that have been really successful in helping learn control in high-dimensional situations like Majoku and Atari fast. The problem with simulations like Majoku and Atari is that there's not actually much visual complexity. Generally, everything happening in the scene is important, and anything that changes is likely important. Now, that is not true in the real world. So in the real world, it is often dominated by visual distractions or like noise in these environments. If you can imagine driving down a street, things like, architecture of buildings, the exact kind of, shapes of clouds in the sky, tree branches, and so forth. A lot of it is junk information. There's only a few things that matter. So basically, one of the things we were kind of wondering is like, can we come up with visual representations that do better than generative models? The more task irrelevant information that we have. And we use this idea of biosimulation metrics. So Ferns et al. In 2004 had this paper to show, can we come up with a functional, like a behavioral distance between two observations here, which is equal to a recursive relationship, which is equal. So it's equal to what was the reward difference given a particular action, or the worst case of actions, together with the next distance. So it's a recursive through time with some kind of discounting. So it's not an infinite number. And so what this does is it says, okay, these two observations are the same if all of the reward differences through time for any action set would be the same. So if the cloud in the sky is changing, that probably changes nothing in terms of the reward. If there is a car in front of us and it disappears, those two observations are very different in terms of the actions we could take that may or may not lead to a collision. And so what we did, so Amy Zhang and some others, including myself, was to basically take that idea and to learn a latent space, to say, can we learn latent space such that distances in latent space are equal, are kind of matched here using this MSE error to this distance between two observations. And so these latent states are really just encodings of observations. And so this is a loss function on an encoder that we can come up with. And so this is how, and so by using the reward function is how we determine what is relevant to the observed system for ultimately controlling well. And so we basically had some Mijoku tasks where we increased the amount of distractions in the background from the original DeepMind control set to this distraction with kind of circles in the background to completely natural images here. And just in the interests of time, I'll skip over the video and show that basically what we saw is in the original setup, things like soft latent actor critic did very well. This is an environment they were designed to, and so this is a reconstruction-based method. But the more, and our method is in green here, but the more distractions we add, the more they kind of equalize. And when we get really distractive, like we've got real images in the background that are incredibly hard to predict and reconstruct, that's where our method starts doing better. And so we can see here what the latent space might look like. So if we've got kind of robots in the same situation, but the backgrounds are very different, the biosimulation latent space can group them very close to each other, but the VAE kind of reconstruction says, well, hold on, most of the pixels are the background and they're very different. So I need to map them to completely different areas. So it's getting distracted by details that just do not matter for control. So onto the good stuff. For autonomous driving, we did a similar thing where we came up with some generic reward function like highway progression and some penalties for steering. And this is what the latent space looks like. So if we were to kind of sample images that generated this latent space here, this t-SNE, this is what it looks like. So we have some samples that are very close to each other in terms of this behavioral latent space. What we see here is that, here we've got like, cloudy sky, shadows, we've got a wall to the right. And here it's very bright and we've got a car to the right. And here it's a bit more overcast and we've got a big truck to the right. Now these things look very different, but behaviorally they're the same. If we turn right, if we go forward a bit and turn to the right, we're going to crash into something that's dangerous, negative reward. If we turn to the left, it's fine. These things are effectively the same state. And we want to be able to take the same actions to better generalize. Some other situations here is just open highway driving. It doesn't really matter if it's overcast or sunny. It's effectively the same state. Over here, we've flipped the car. And it doesn't really matter what time of day it is, it's still a negative reward. And so here's a kind of image where we replayed, video where we replayed the same movements of all of the cars, but the weather has changed. So we're either in a sunny situation or a cloudy situation or sunset, so it's kind of more pink. And you can see the in latent space, this 8D latent space. So we've got like Z1, Z2, Z3, Z4, so forth. We've got the sunny, cloudy, and sunset representations where they're encoding to. And you can notice that they're mostly sticking together. So the model has understood that these situations, even though very visually different, are in fact the same. And some experiments that I haven't shown in this but are in the work is to say, what happens when you have out of distribution changes in things like the background or weather. And because the model has learned to desensitize itself to things like, in the background sky and so forth, it will be robust to that even at test time, even if it's never seen this thing before. So, these things do happen. Last year in California, we had a big fire, and one day we woke up and the sky was just bright orange, and it was very strange. But things like that shouldn't necessarily change the way we drive if it's not critical to planning. And so we can learn desensitivity through some of these techniques. Okay, I think in the interest of time, I'll wrap up here. But yeah, thank you very much. And if there's any questions, please go ahead.
Yeah, thanks. I think that was just an absolutely amazing talk. Very interesting. Very, very interesting. So I have a question, but I think I'll just save it for the panel discussion. Boris has a question on, is it possible that optimizing for prediction accuracy on agents relevant to planning can actually hurt OOD robustness? One reason for that is that instead of asking the neural net to learn the general motion dynamics of the environment, you're asking it to optimize for a specific set of scenarios that frequently occur in front of an AV, which might allow for more shortcuts.
Allow for more shortcuts. Yeah, it's an interesting question. The assumption. So I think the case of OOD that we're protecting against is the case of things that happen in terms of the pedestrians that were already irrelevant. So if they do something crazy, but they're not necessarily right in front of the vehicle, then the if they do something crazy that we didn't really predict at test time, but that the model wasn't necessarily interested in the first place, like their attention weight wasn't that great, then at least the model will not get essentially, there'll potentially be less likelihood that the model will have some crazy output given this crazy input that it's never seen, if it's already learned to suppress that input. But yes, it's not foolproof. If something OOD does happen around one of the pedestrians that is more likely to cause the car to brake or not, then yeah, it's not a full protection against all types of OOD. Right. I hope that answered the question.
So second and probably last question from Dev Vidani is that could you share your view on what model would work practically? What metric makes most sense, even though collisions went down drastically with most conversion model max over YK? Which model is most practical for real life scenarios, and how to decide on that amongst multiple models you shared?
Yeah, that's a great question. The honest answer is I don't know. We thought about this for a while, and we're originally trying to publish on a metric rather than a method. But yeah, ultimately, I don't know. One of the things we had thought was if we do have a probabilistic planner, and we assume that so if we make the assumption that the plan is always probabilistic, can we instead score the likelihood of the action under the can we match the can we evaluate the likelihood of the ground truth action that the vehicle actually took in the training distribution under the prediction on what the car will do given its predictions of what the pedestrians will do. Sorry if that's a bit confusing, but basically the idea there was, can we use the likelihood of the ego vehicle's actions as opposed to the likelihood of state trajectories? And I think that is likely something that's a bit more easy to justify than these variations of kind of methods that we came up with. We did try optimizing that, and it turns out that that was a terrible thing to optimize, but it may not be a terrible metric. It may just be a terrible loss.